Hello, my name is Rodrigo Rezende. I'm professor from the postgraduate program in biotechnology from the University of Araraquara, Uniara, Brazil. And today we will have an interesting lecture from Professor Dr. Ângela Maria Moraes. She is graduated in chemical engineering at the State University of Maringá, Brazil, and obtained her PhD from the University of Campinas, also Brazil, in a joint project with the North Carolina State University, United States. She is a full professor at the Department of Engineering of Materials and of Bioprocesses at the School of Chemical Engineering at the University of Campinas, Unicamp, and works in the areas of tissue engineering, biopharmaceuticals, and biomaterials since 1992. The main areas focused by Dr. Ângela Moraes are the production of wound dressing for skin lesions and of vehicles for the controlled release of bioactive agents, as well as the expression of recombinant proteins through animal cell culture, along with skin, vascular, bone, and cartilage tissue engineering. Currently, she is the Vice Dean of the School of Chemical Engineering at Unicamp. The title of her presentation will be Polysaccharides in Tissue Engineering, Biofabrication and Bioprinting, When and Why to Use. So, I would like to give welcome Professor Dr. Ângela Maria Moraes. It's a great pleasure to have you here this day. I'm sure that your talk is very stimulating one and will bring very good information for everybody. Hello.
Thank you very much, Rodrigo. It is a pleasure indeed to be here to talk to you today about a topic that I have been working with for such a long time. And I would like very much to thank the organizing committee of the first International Digital Congress on 3D Biofabrication and Bioprinting. I thought that I should start showing to you a little bit of the university I come from. It's called Unicamp, as Rodrigo already mentioned. It is in the state of São Paulo, in this marked in this yellow dot. It is a quite young university. We were founded in 1966. We have over 2,000 faculty members. We have 66 undergraduate programs with more than 20,000 students. We have 155 graduate programs with over 17,000 students and around 1,400 extension courses with over 11,000 students enrolled. And my talk will be divided, in fact, in three parts. In the first part, we will talk about polysaccharides and tissue engineering as a whole. I'll show you the reasons to support the use of polysaccharides in tissue engineering, biofabrication, and bioprinting. We will see a bit of the polysaccharides and their main characteristics. We will also talk about major limitations of polysaccharides and examples of strategies to circumvent them. In the second part, I will share with you some of the developments that we have been doing in the lab I coordinate at Unicamp, LEBC. We'll talk about basically 2 points: polysaccharide-based biomaterials to treat skin lesions and cellularized polysaccharidic biomaterials for cartilage tissue engineering. I'll give you also a very brief overview of other applications we are working with recently. And I will finish the presentation with some final remarks. So, starting with the first part, we have to remember what tissue engineering, biofabrication, and bioprinting have in common. In fact, bioprinting is one of the strategies of biofabrication, and biofabrication is one of the many different approaches that we can use to develop materials for tissue engineering and regenerative medicine. So, scaffolds for cell growth are very important in this regard. And we can use different classes of components to produce biomaterials and scaffolds as a whole for tissue engineering, such as metals, polymers, ceramic materials, bioactive agents, for instance, to improve their performance. Sometimes we even have to have mixtures of these compounds, such as in composites or hybrids, which are mixed respectively in a micrometric scale and at the nanoscale. Sometimes we have to produce layered materials with these components to attain products that will meet our goals. And regarding specifically polymers, we can use polymers that are synthetic, or we can use polymers that are nature-derived, such as nucleic acids, proteins, collagens, for instance, is a protein that is very much used to produce scaffolds, and polysaccharides, that will be the topic of our conversation today. Polysaccharides are normally composed of more than 20 monosaccharides, and they can be derived from animals, such as chitin, chitosan, or hyaluronic acid. They can be also derived from plants, such as cellulose, pectins, and starch, and they can be derived from seaweeds, for instance, alginate, carrageenan, agarose, fucans, or even from microorganisms cultured in bioreactors, for instance, such as hyaluronic acid that we just mentioned, that can be also obtained directly from animals, xanthan gum, gellan gum, and glucans. These types of polysaccharides are quite interesting because since we can produce them in bioreactors, we can have a more controlled product regarding, for instance, quality issues. The polysaccharides release monosaccharides or their derivatives by complete acid hydrolysis or by the action of specific enzymes. And the predominant unit released is the glucose. The polysaccharides can differ by the type of monosaccharide unit that they form them. For instance, as we show here, we have polysaccharide with 2 different monomers, or here we have with 3 different monomers. They can also differ regarding the length of chains and the degree of branching, as we have here, for instance, a branched molecule and an unbranched molecule. And these have strong implications on the solubility, on the reactivity, and the viscosity of the polysaccharides. Some general structural characteristics of polysaccharides are listed below. We can see that they have a very high molar weight. They have a high number of OH groups, and because of this, they have a tendency to form intra and interchain hydrogen bonds, which in turn result in solubility reduction. That implies in the formation of aggregates in solution, but it also gives us a good film-forming property of this type of molecules. They are also slightly hydrophobic because of their CH groups. They form stereoregular structures with semi-rigid helical conformation in solution, as we show here for amylose structure in water. And their stability can be dependent on the temperature, such as in the case of carboxymethylcellulose, or dependent also of the presence of ions, such as alginate, in the presence of calcium ions that can form a gel. Many attractive characteristics of the polysaccharides will make them interesting as components of biomaterials, such as the fact that they are renewable and sustainable, because they can be derived from nature, or they can be derived from reactions in bioreactors by microorganisms. They are very biocompatible because they have a low content of antigenic determinants, and also because they mimic extracellular matrix components, such as the glycosaminoglycans that we find in cartilage. Here, for instance, we can see the similarity, the structural similarity of chitosan with two of these glycosaminoglycans that we find in cartilage that are chondroitin 4-sulfate and hyaluronate. They can also be degradable or dissolved in vivo by some enzymes that we normally have. And they may be processed as particles, powder, films, and gels, allowing us to obtain a different set of products. However, they also have some limitations. One of the most important is the lot-to-lot variability in composition in molar weight, because they are not synthetic, so sometimes when you obtain them directly from animals, for instance, we have to do a lot of purification protocols to have a material that has not such a variation and that does not bring contaminants to the final product. Sometimes they can also show low mechanical and water barrier properties, and due to their strong hydrophilic behavior, they may cause premature structural disruption of the structure of the construct inside the body, and they also form viscous solutions that are sometimes a little bit difficult to work with. And here we have also some examples of solutions that we can adopt to circumvent these limitations, such as the development of quality standardization processes to improve the lot-to-lot variability. We can use polysaccharide-based blends and composites, for instance, to improve mechanical and water barrier properties, and we can even functionalize the polysaccharides via polymer grafting to better meet the requirements of our designed product. But what can we produce with polysaccharides? So now we go to the second part of my talk, that I will share with you some of the developments that we have been doing over the last 2 decades. So starting with the skin lesion materials, first of all, we have to think about the characteristics of the ideal dressing and scaffolds for skin wounds. In my lab, we normally work a lot in this sense with the production of dense and porous polysaccharide-based biomaterials to treat these types of lesions. And for that, the materials should be non-toxic and biocompatible. They should be able to work as a microbial barrier. They should allow gas exchange and expate of the exudate, that is a liquid that is produced in the lesions. The material should also be flexible and fit to the body contours. It should be adherent without requiring adhesives. Ideally, it should also contribute to reduce pain and to promote the healing process. So a long set of requirements that we have to meet when producing these types of materials. And then the goals on the development of wound dressings in the labs I coordinate are related to establishing reproducible and easily upscalable methods to obtain uniform polysaccharide-based films and membranes that are designed for the therapy of skin lesions. So over the years, we have studied the effects of many process variables on membrane properties. For instance, we studied the type of polysaccharide to be combined with chitosan. We normally use chitosan as one of our base polysaccharides because of its very interesting properties for skin wounds. We studied the effects of the polysaccharide mass fractions on the structure of the materials. We studied the flow and mixing rates during polysaccharide mixture. We studied the addition of porogenic agents to obtain not only dense but also porous films and membranes. We incorporate and study also the release of different types of therapeutic agents, such as antimicrobial agents, antibiotics, and anti-inflammatory compounds. We also study the sterilization methods that are more appropriate for each type of material. and mechanical resistance reinforcement strategies, such as blending and compositing with synthetic and other natural polymers. So one of the first works that we have developed in my lab is focused in obtaining polyelectrolyte complexes or packs, in which we use chitosan as a polymer with a positive charge depending on the pH because of the amino groups, and we complex then these molecules that are polyelectrolytes, positively charged polyelectrolytes, with alginate that can be also a polyanion because it has many carboxyl groups in its composition. So we have the main interaction here as electrostatic attraction between the amino groups and the carboxyl groups, and we can use alginate, we can use many different other types of polyanions, such as also xanthangum here, that we also show a carboxyl group. In some cases, we can even further stabilize the structure by complexing the remaining groups of carboxyl for instance, from alginate that were not bound to chitosan and have a more reinforced material. We normally produce fibers such as we observe here in this image. And when we studied over 10 years ago the characteristics of membranes that we can prepare using a flow rate of 40 millimeters per hour of chitosan added to a solution of alginate that is mixed very, very slowly, we noticed that we obtained a set of very interesting properties for these membranes. They had this aspect, so it is a layered, natural layered aspect, and they were very thin. They had only about 80 micrometers in thickness, so it would be very comfortable for the patients to use it. It swelled a lot in aqueous solutions, absorbing, for instance, 19 grams per gram of water. It had a very nice water draining rate of about 13,000 grams per square meter day, and a high also water vapor permeation rate of almost 3,000 grams per square meter day. We noticed an oxygen permeation rate of 40 mL of oxygen per square meter day, and mechanical properties regarding tensile strength of almost 30 megapascal, and an elongation at break of about 8%. We were not quite satisfied with the mechanical properties regarding elongation at break, because in spite of having very nice mechanical properties regarding tensile strength, the normal skin, for instance, has a tensile strength of around 30 up to 30 megapascal. The elongation at break should be higher. So we focused some of our studies that I will show you in a bit regarding this topic. These membranes were able to support very well the growth of viral cells on its surface. We can see here, for instance, that the cells, they not only grow and proliferate, but they also form an extracellular matrix. We can see here in these black arrows that we have fibrillar material produced by the cells to better fixate them on the surface of the material. And we analyzed the efficacy of these membranes to prevent microbial growth. So since chitosan already has by itself antimicrobial properties, we thought that these membranes would probably form an inhibition zone. It would liberate some components that could inhibit the growth of two different types of bacteria that are normally seen profusely in some types of skin lesions that are Pseudomonas aeruginosa and Staphylococcus aureus. However, since the amino groups of chitosan were combined to the carboxyl groups of alginate, we saw no inhibition zones, as we can see here in the image. However, when we applied these membranes on the top of an agar medium, and we put some drops of a very concentrated suspension of the bacteria on top of the membranes, we observed that there was no growth of the cells through the membranes. So these membranes have a very high potential to be used as barriers to avoid contamination from the environment. But if we wanted it to have an antimicrobial activity, we should then add an antimicrobial agent to its formulation to improve this particular goal. And we did that. We just added to the membranes a compound that is shown here. It's a very complex compound that releases slowly silver ions that are bactericidal. This compound is called alphasan RC2000, and it is a silver sodium hydrogen zirconium phosphate. It contains about 10% silver. We developed this work in a partnership with a company here in Brazil, LM Pharma, from São José dos Campos. And we observed that by just adding these components, what we saw before was totally circumvented now. We saw inhibition zone of 4 millimeters for Pseudomonas aeruginosa and of 6 millimeters for Staphylococcus aureus. So very nice effects from satisfactory to highly satisfactory to these two types of cells. And when in contact with these membranes, the solutions of these and other types of cells also suspensions, of these types of cells. After 1 hour, we noticed a very significant reduction in the population, even for a multi-resistant strain of Staphylococcus aureus. However, when we were developing this new formulation with alphasan, we observed that when we added the silver-containing component, we had a very significant drop in the tensile strength. Elongation at break remained low, but the tensile strength reduced a lot. So what we did was to add to this new formulation a silicone gel that is Silpuran 21AB. And we noticed that we could not only reach the original levels of tensile strength, but even to be above it. The elongation at break, however, remained low. Here we can see the aspect of the membranes containing this Silpuran 2130AB. Since this compound is very hydrophobic, in fact, it does not mix well with the polyelectrolyte suspension, but instead it forms like little droplets in the structure. So here we can see marked for silicon, these small droplets spread over the structure, and here the droplets and also the aggregates of the drug inside the material. And not only then we reached a higher tensile strength, but we had an extra gain that was an increase in membrane flexibility and adhesiveness, because Silpuran is a tacky polymer, so we could transfer some of this interesting property also to our membranes. We were still concerned about the elongation at break that was low, but then we thought that all the tests that we have been doing so far were performed in dry conditions. And when we are in contact with the lesion, we have the membranes being wet by the exudate. So we decided to check the effect of relative humidity in the membranes, and we noticed that we have a bit of a drop in tensile strength with increase of humidity, but we also noticed that we have a significant increase in elongation at break. And we noticed then that formulations combining chitosan and alginate or chitosan and guar gum were better regarding tensile strength, while formulations combining chitosan and xanthan gum or chitosan and guar gum were better regarding elongation at break in moist conditions. Afterwards, we analyzed it then. We thought about analyzing the effect of compositing these types of membranes with fibers to try to improve the elongation at break. And we analyzed the effect then of linen fiber in different orientations, as we show here for dense or porous membranes. We had the fibers in parallel, crossed, and random orientation, and we saw that we could in fact improve significantly the elongation at break, comparing to the controls, and reaching almost 22% in the case of fiber orientation in a crossed way in the dense membranes. Another way of improving elongation at break was to, instead of exploring the PEC compounds of alginate and chitosan, for instance, we decided to do multi-layered membranes. So we produced by electrospinning polycaprolactone and cellulose acetate materials that were covered with many subsequent layers of chitosan and polyethylene oxide. Polyethylene oxide was added to turn chitosan a little bit more easier to electrospin. And we can see here that we have a very high difference between the diameters of the fibers formed by PCl and cellulose acetate when compared to chitosan and PEO. And we noticed, in fact, that the elongation at break was significantly increased in this case. We had over 430% of elongation at break. So we decided also to test other strategies involving electrospinning. We produced some hybrid dressings, and these dressings, in addition to improve the microenvironment control of the lesion, because we have a more open structure than we see with the chitosan alginate membranes, for instance. So we can have higher breathability and higher also water vapor transmission rates. We decided to produce the PCl matrix by electrospinning and then to coat this with a layer of alginate solution containing a plant extract that has anti-inflammatory action, that is Rabidia chica. And here we can see the type of material that we had. So we improved at the same time the microenvironment control and bioactivity of the material. And we noticed that in this case, the elongation at break was also very high, of almost 200%. But going back to membranes that are produced by using the PEC approach, we tested the dense and porous structures produced by mixing chitosan and xanthan gum as scaffolds for mesenchymal stromal cells. And we could see that in both situations, the cells, similarly to what we noticed for the viral cells, they grew quite well. They produced a profuse extracellular matrix. And we then tested these materials in animals. We tested with the dense formulations, because the dense formulations were very transparent. This is a membrane on top of the word transparent, just to give you an idea. And this would allow us to observe what would happen to the animal, to the wound, without the need of removing the dressing. So it was quite interesting. We did 4 types of experiments. We had a control experiment in which the lesions were only treated with saline. We had another one in which the lesions were treated with the membrane. We can see here the membrane, and you can observe that the lesion is very clear. We do not need to remove the membrane to observe what's going below it. Here we tested only adding the cells, and here we added the cells that were cultured on the top of the membrane, of the dense membranes. We observed that wound healing is significantly higher with the cells here, and independently of the membrane, of the presence of the membrane. However, the cells on the membrane are much easier to apply, because here, for instance, when you put the cells only, they can just spread through other areas of the animal. And as we had seen before, membranes can protect the wound against environmental contaminants because they have a barrier property. So the results were quite nice for this formulation. And now I will talk to you a little bit about the developments we have been making in our labs in studies on cartilage tissue for osteoarthritis. We can see that we have here a healthy knee, and here we have an osteoarthritic knee showing eroded cartilage and also eroded bone. And this degeneration then of both bone and cartilage in very serious cases can lead to structural and functional failures. The incidence, in fact, of osteoarthritis in a population over 65 years old is quite high, is about 30%, and it is the most common cause of motor disability in adults. And we have indeed several treatments, but they are no definite solutions for this problem. They are only palliative solutions in most of the cases. So a promising approach to deal with that is tissue engineering, in which we analyzed in our lab 2 different types of approach: cellularized thermosensitive gels and 3D bioprinting. So in the first case, we developed carbohydrate-based thermosensitive hydrogels by mixing methyl cellulose, xanthan gum, and carboxymethyl chitosan. We kept xanthan gum because of its very interesting rheological properties, chitosan because of its interesting properties regarding wound healing, and methyl cellulose to have the material thermosensitive. And we added 3 types of drugs too: sodium diclofenac, gallic acid, and dexamethasone. Sodium diclofenac and dexamethasone have anti-inflammatory activity, and gallic acid can form bonds between chitosan molecules, or also between collagen molecules in the cartilage when applied to the cartilage. So it would improve the structure of the material once injected. So we produced the materials. We did several types of characterizations, mostly rheological characterizations. In the most promising formulations, we cultured dental pulp stem cells. We analyzed these cultures to see if the cells could be differentiated to chondrocytes, and then in this sense, afterwards we could inject these formulations inside the lesions directly without needing surgeries, in a less invasive approach. So our targeted gelling temperature was between 22 and 37 degrees C, because 22 is about the temperature of the surgical center, and 37 degrees C is the temperature of the body. We observed for 3 different formulations that we could reach this temperature. We had for this one containing 10% of methyl cellulose and 0.5% of xanthan gum and carboxymethyl cellulose, a temperature of 27 degrees C. A gelling temperature for this one, free of xanthan gum, of 31 degrees C, and this one free of carboxymethyl chitosan, 24 degrees C. We can see here in room temperature they are in the liquid form, and at 37 degrees C they gel. And we cultured the stem cells in these hydrogels. We observed no significant decrease in cell viability after 7 days. We noticed that after 14 days, the cell concentration decreased about 3 times inside the gels. However, we noticed that there was cell migration in these swollen matrices. So they were running away from the matrix to the surrounding culture media. They were not dead, in fact. And we noticed that the cells that were retained in the hydrogels were capable of growing for up to 28 days. Then we still have not tested in vivo these formulations, and we have to do some more tests because these are very recent results. We attained those this year, so we will be working on these in the near future. Another work that we developed was on bioprinting spheroid-containing hydrogels to produce chondral structures. So the idea was to do here a CAD design of a structure, to bioprint it, to try to mimic the structure that we would have for substituting part of a cartilage. In this case, the medical intervention should be a bit more aggressive. It should have, it should involve an implantation of the obtained material, not an injection. And our idea was that 3D cell organization in vitro as spheroids can more closely mimic the natural environment of organs and tissues, as we show here. However, the complexity of these cultures are significantly higher than what we have in monolayer and 2D culture. And the idea is then to use the spheroids as building blocks for tissue engineering. So each spheroid is like a brick that we can use to build a wall. And it's very important for that you have similar spheroids regarding size and concentration, cell concentration. So we started our work on developing a micromolded non-adhesive hydrogel in which we first developed a mold in which we would pour a hydrogel solution and form a structure like this one, in which we could deposit a controlled amount of cells that could give us a controlled size of spheroids. And so this is the idea behind the whole process. We would get cells, for instance, from the patient, we would expand them, we would form a working bank with it, and then we would have them ready to be mixed with our device. And the device was then produced like this. We had the mold produced in a resin cast, to which we would pour a sterile agarose solution. Agarose is, as I already mentioned, a polysaccharide too. And then we would have this material being casted inside this resin cast, like in a negative cast. We would decast it, and then we would transfer that to a multi-well plate together with the cells. And after, here we can see the cells deposited in the microcavities. And after 3 to 5 days, we would obtain about 164 spheroids per well of these casts, of these agarose casts. In fact, we observed that we obtained very dense and compact structures with a mean sphericity around 92%. We obtained 75% of the spheroids in diameters from 300 to 400 micrometers. And these would show us that the spheroids had the potential to show necrotic cores. Because of that, we reduced cell concentration, and then we were able to achieve very highly viable spheroids with lower size in the range of 200 to 300 micrometers. Here we show characterization of these dental pulp stem cell spheroids after 7 days with different markers of cell viability, of nucleus, and of proliferation. We can see that they are very healthy. And we tested this device and this approach also for other human stem and differentiated cells, such as amniotic fluid stem cells, for chondrocytes, embryonic stem cells, and mesenchymal stem cells. But we had to print that, so we formulated a bio ink based on alginate and xanthangum. We observed that the rheological behavior of this mixture was different from what is considered the gold standard Nivea cream, but we were still able to print a complex structure. We noticed also that sterilization tended to reduce printing accuracy in about 30%, so we had to readjust the formulation of the bio ink, and we can cross-link this material using strontium chloride, and we noticed not a significant reduction in cell viability. Here I can show you the printing that we attained with this type of material. And here I show you very quickly the material morphology, printability, and stability. Here is a 4-layer material. We can't see the pores in this augmentation of the image, but here we can observe that we preserved somehow the pores that we aimed at. And this is a printing already with the spheroids. So just to finish a little bit of other recent developments that we have been working on in our lab. We have the study of 3D structures obtained by complexation of chitosan, for instance, with pectin for vascular tissue engineering. So here you can see that we can obtain these materials also in a cylindrical, open cylindrical form in which the cells grow quite nicely. We produced the phosphorylated chitosan xanthangum scaffolds for periosteum-guided bone tissue regeneration. Here we can see that this membrane, that in this case chitosan was modified to add a phosphorylated group to improve mineralization. We also analyzed films loaded with imiquimod for controlled release in mucosal environment. And we are analyzing also the incorporation of doxycycline in hydroxyapatite chitosan xanthangum membrane composites for buccal tissue regeneration. So very different approaches in here. Then, as my final remarks, I would like to give you the final message that polysaccharides can indeed be very successfully used to produce biomaterials with relevant properties for human health, different types of polysaccharides and also different types of techniques. We have still many opportunities that can be explored to develop new polysaccharide-based biomaterials with improved formulations and properties. There is a whole universe there still to be explored. I'd like to acknowledge the support over the years of all the companies and the agencies that financially supported the work, to my colleagues at the Unicamp from other schools than chemical engineering. I would like also to acknowledge the help of many collaborators from abroad, from Portugal, Colombia, USA, Canada, Ireland, the Netherlands, and also from other universities here in Brazil and research centers. So I thank you all very much for the collaboration. And here are all the students that have been contributing over the years. Here in pink are the students that are working currently in our group. So soon we will probably have more results to share with you. And I'd like to finish the presentation with my contact and a bit of the pictures of the School of Chemical Engineering at Unicamp for you to have an idea. Thank you very much for your attention.
Hi, Ângela. Thank you for your nice presentation. It's always very good to me to watch your lectures, and also giving us much news. And so I can see that you are strongly going through or towards bioprinting. So I can see that you use this mixture of technologies as casting, coating, electrospinning, and also bioprinting, and also using your rich samples of biomaterials, of natural and mainly polysaccharides. I think this is very interesting for everybody to see, and I'm very glad to see this presentation. And I would like to ask you quickly, what about this sensitive, thermosensitive carbohydrate based materials? If you are using for or thinking of using them to bioprinting as 4D bioprinting.
Yeah, we wondered about that. We did not do that yet because we do not have the printer that would be would have like the collecting part at a higher temperature, because we would have then to have a special printer that we still do not have. But it is in our goal to test that too, because the hydrogel is quite interesting.
Okay, Ângela. So I would like to invite everybody to visit your page and your curriculum, which is available in our 3DBB website. And so I think Ângela will be very pleased to get some question later or some other information. She is always lovely, a lovely person. So Ângela, I would like to thank you again. A great pleasure to have you here this day. Okay.
My pleasure. Thank you very much for the invitation.
Thank you.